Well, it's time. So let us start the second lecture of Charles Bordenave. I will put an announce again in the chat so in the chat in minutes I will put an announce for everybody with the slides of yesterday and some more detail for students who want a credit. So maybe Charles will make another announcement, but basically what students who want a credit are expected to do is to write to Charles Bordenave, perhaps with his main copy, and ask him to give you a homework, basically. So, yeah. So Charles, please.
Okay, so what we have done so far, we have seen we have defined the adjacency operator. We had a graph with a countable set of vertices, which is locally finite, meaning that all vertices have a finite number of adjacent vertices. Okay, and when you are in this setup, you can define at least for compactly supported functions, compactly supported vectors of L2. You can define the adjacency operator by just the usual formula. Okay, by this formula. Okay, so this is for X in V. And when this operator happens to be essentially self-adjoint, in particular, which is the case that we should focus on when the degrees are bounded, essentially self-adjoint, then we can define a probability as a spectral measure of the vector, which satisfies a spectral measure, which you can write formally as like that, which is for a vector phi of compactly support. You can define a measure which will be equal to the indicator of E of A of phi for E Borel set in R. Okay. And for example, when A is bounded, you can, when A is bounded, if A is bounded, if A is a bounded operator, so when the degrees are finite, and in other cases when the moments make sense, you can define the moments of this measure. Let's point it at a vector. Then there are the moments of the powers of your operator A, and this has a nice combinatorial interpretation as a number of closed walks in the graph G of length K, starting at X. Okay. Okay, so when the graph was bound, so when the graph is finite, if G is finite, this spectral measure as a particularly simple form is just the sum over the direct mass of the eigenvalues of the projection of the vector phi on the corresponding eigenspaces. Okay, where λ1, λi are the eigenvalues, and ui an orthonormal basis of eigenvectors. Okay. And when J is finite, we also define the empirical spectral distribution, which we was only denoting by mu G without the vectors phi. So which is simply the sum of the direct mass of the eigenvalues, which is for us, which is interesting because you can rewrite it as a spatial average over all vertices of this spectral measure at a given at vectors. Okay. Okay, so we made some computations. So I mentioned, so when now we can extend this definition of average spectral measure or spectral measure. Where is my so we used to call that average spectral measure. Average spectral measure. Okay, and if G is a Cayley graph of some group, finitely generated group, then, or more generally, when G is a transitive graph, G is transitive. In particular, mu G of delta X does not depend on X. Does not depend on X. Okay, because this is the moments, for example, are just the number of closed walks of length K starting from X, but since the graph is transitive, you apply this cannot depend on X. Okay, so we simply define mu G, which was again defined as being the spectral measure at, for example, the unit of the group. Okay, and this is called in this context the Plancherel measure. Okay, so if the group is finite, then both definitions coincide. Okay, because of this remark that mu G of delta X does not depend on X. Okay, so defining the spectral measure, the average spectral measure, in this way or this way is consistent when you have a finite Cayley graph. Okay, so now we will do some computations of explicit expression of Cayley spectral measures. Example of spectral measures of Cayley graphs. Okay, there are it's a kind of big deal in to try to compute spectral measures of Cayley graphs, because as I said last time, but we'll come back to that, the adjacency operator is an element of the group algebra, and these Plancherel measures are of prime importance for in the study of those groups. Okay, and in particular, you are particularly interested by the computation of atoms. Okay, so let's start with a simple example, which we have already seen so far. If you look at the graph of Z, okay, so this graph, you can write it as a Cayley graph, if you want to be formal, the additive group, the Cayley graph Z of Z with the generators plus minus, okay? This is, I will simply denoted by Z. Okay, so if you compute the spectrum, like to compute the spectral measure of a B infinite pass, if you want, of a bi infinite pass, what is we already computed it, I think, or this is again this is this arc sine law. No, we didn't compute it, but it's a nice exercise to compute that formula. Okay, so this is the arc sine law. Okay, we saw that for the segment, if you are computing the limit of the line segment or the circle of size n, this was the limit of the spectral measure was this arc sine law. Okay, so for if you want to compute the Euclidean lattice, okay, mu of ZD from what we saw last time will be the usual convolution d times of this arcsine. Usual convolution. Okay. If there were some computations of the free group, if you look at the free group with its let's call it FD. No, let's not do. Let's look at the. Let's call TD to be the infinite irregular tree. Okay, so here I'm trying to make d equal to 3. Okay, of course it continues for a long time. Okay, you have some note here. So TD, you can write it as it is a Cayley graph. If D is even, if D is 2K, this is a Cayley graph of the free group FQ with Q generators and their inverses with its natural set of generators. Natural set of generators. Okay, what does it mean is, and if D is, so it means that, for example, if you have two words, G1, G2, G1 minus 1 and G2 minus 1, so you start from the empty word. So for example, when you go here, you multiply by G1, here by G1 minus 1, here you multiply by G2, G2 minus 1, here you continue to multiply by G1, G1 minus 1, and so on. And you will the picture that you will get is an infinite 4 regular tree. Okay, so this is F4, T4, F2, which corresponds to the F2, which will correspond to the to T4. Okay, 4 regular tree. For D odd, you can also interpret that as a Cayley graph of a group. It's a Cayley graph of in general, TD is a Cayley graph of you take Z over 2Z, you take the free product of that D times with the natural and with the free with it, and you take the generators, the natural free generators. I invite you to check that. Okay, whatever. So TD is certainly this infinite irregular tree is so it is a transitive, infinite transitive graph where you can compute explicitly its spectral measure, and it has a density against it has some density with respect to the Lebesgue measure, and it is given by this formula: 4 times d minus 1 minus x squared divided by d squared minus x squared, indicator of modulus of x less than 2 square root of d minus 1 dx. This was computed by Henry Kestel in his PhD thesis, so I think it was somewhere in the 50s. And this law is called sometimes the Kestel, or usually the Kestel-McKay formula. So Kestel computed it in the 50s, but McKay, who did not, in the 80s, who did not know the work of Kestel, recomputed this formula. There is an interpretation in terms of, we saw this free product of groups. In fact, so if from this formula, the spectral measure, you can interpret that as being let's call it Q, maybe not Q, it's not right. if pi is 1/2 of the Dirac mass at 1 plus 1/2 of the Dirac mass at -1, so it's a Rademacher distribution, which is equal to 1 with probability 1/2 and -1 with probability 1/2, then you can write pi is not a great number. It's the free convolution taken d times of pi, because pi is the spectral measure of z over 2z, as you can check. Z over 2z. Pi is the spectral measure of z over 2z because z over 2z, the adjacency operator, is trivial. Okay, as a graph, it looks like that. The adjacency operator is this one, and there are two eigenvalues, 1 and -1. Okay, and if you believe that the tree is a Cayley graph of the free product of d copies of that guy, we saw last time that the spectral measure should be the convolution d times of this measure. And you can also remark that the arc-sine law corresponds to the free product of pi 2 times. The arc-sine law. Maybe I should write mu of z. Okay, so all these examples were have led, which were known for a long time, have led wrong conjectures because people thought that when you have a Cayley graph, all spectral measures should have no atoms, okay, or maybe a finite number of atoms and stuff like that. And then came a counterexample, which is very important for the development of this theory, because it shows that there is the regularity of the spectral measure is necessarily a subtle topic. Okay, and this example comes from a kind of exotic group, which is called the Lamplighter group. Lamplighter group, which I will now explain in details. Okay, so there were the three groups. This case, and the like. So the Lamplighter group. Okay, so this example was made in an important paper by Grigorchuk and Zuk. I think it was in the 90s, if I remember. And there is also some development. The paper of Grigorchuk and Zuk it has been improved by Lehner, Neuhauser, and Voss later on. And I will focus on the presentation of the Lamplighter group as made by Lehner, Neuhauser, and Voss. Okay, so this Lamplighter group. They have given two examples. They have given an example of, as you will see, give examples of a Plancherel measure which is purely atomic. Okay, so it's a group, it's an infinite group, so it's a countable. Of course, if the group is finite, the Plancherel measure has to be purely atomic. But as you will see, it's a group with an infinite number of elements. So it has given an example of a Plancherel measure which is purely atomic, and also of a spectral measure, a Plancherel measure, let's call it mu g, and also such that even that the atom at 0 can be any number in 0, 1, because there was a conjecture by Atiyah, which was, so he disproved the conjecture, a conjecture of Atiyah, that the atoms should be, I think, maybe algebraic numbers. Okay, but in fact, it can be even, it can be transcendent numbers. Okay, so this result is due to Austin and also Lehner and Wagner. Lehner and Wagner. Okay, so I will try to explain you how you do the two things. Okay. So even if the Lamplighter groups are a bit exotic to my, at least at my level of knowledge, but they provide a very, very nice counterexamples of what you could think as being should be properties of nice transitive graphs such as Cayley graphs. Okay, so let's go with the definition. So you take you start with a gamma, which will be a finitely generated group. Finitely generating group, which is it's called sometimes, as you will see why, the work space. Okay, and okay, I will not do for you the general Lamplighter group, but almost as general as possible. So, and then you take a lump space, which for me will be Z over NZ. Okay, which is called the lump space. Okay. So what I will do, I will first define for you the group operation, and then obviously you will be a bit lost, and I will make, and then it's better explain when you do a picture, and hopefully you will understand what this group is about. So the Lamplighter group is a rest product of the lump space and a gamma. Okay. So this is the Lamplighter group. So it's a rest product of two groups. So this rest product is a strange product. It's a strange group product which I will define for you. So it's a group on the set. So what is an element of this Lamplighter group? It's an element of L power gamma cross gamma. Okay. So the interpretation is that eta X belongs to lambda, okay, is the Lamplighter group where eta belongs to L power gamma, is a configuration of lamps. It's a configuration, so you can see that as a function from gamma to L. Okay, so the lamp has n colors in my setting. Okay, so to each group element you attach a lamp, the color of a lamp, an element of L. Okay, and X, which is an element of the group, is the position of the Lamplighter. Now I will make a picture. You have to imagine that if I take gamma to be Z and n equal to 2, so I have two okay. So here is let's say black and white denotes the color, and so this is a configuration eta, and also I should also point a direction, a distinguished element of Z, which is the position of the worker. So this is an element of lambda, okay, a graphical representation. So I have a set of lamps which are on or off here because n equal to 2. And there is also a distinguished element of gamma, which is a position, which I interpret as a position of the worker. Okay, so this is called Lamplighter because you have to imagine that the position is a Lamplighter, someone which switch on and off the lamps, and in a street, which is a group. Okay, and there are n positions for the lamps, which is this lamp space. Okay, so I should define a group now, the operation on the group. So eta X, the product of an eta prime X prime. What is it? So I will write the formula and make a comment, and it should be clear. Okay, so let's look at the position. So in the position of the Lamplighter, you just multiply X and X prime. So that's the usual multiplication on gamma. And then for the position of the lamps, what you do is you add the two configuration, but you shift the configuration, the second configuration, eta prime, by you shift eta prime by the position of the lamplighter at x. Okay, well, so theta x of eta of y is eta of x minus 1 y. Okay, so theta x eta shifts the configuration eta by x. Okay, where you multiply everything on the left by x. Okay, so that's the multiplication. So there are some generators where you can see what you can picture easily. It's so zero. Let's call zero. There should be a unit, which we call what did I do? I think I called it epsilon, which is the empty. All lamps are set to zero, and the worker is at the let's call zero the unit of. I don't know, maybe E. I think I did it by E. Let's call E the unit of gamma. Okay. So the unit of this is a unit of the lamplighter. Cool. Okay, so the work element is you take x in gamma, is simply you multiply the empty configuration of lamps, and but the worker is at position x. This is called a work element, and a switch element, which is also which you can write as L, the Dirac mass at 0. Okay, where so L Dirac mass at 0 means that Dirac mass at 0 is a configuration where this is 0 everywhere except at 0. It's an indicator that y is equal to 0. So it's the usual Dirac mass. Okay, so these two operations, they generate a group. So what does Wx means? So eta x, when you multiply it by Wy, what does it do? It does not modify the configuration, but it shifts the position of the worker to y. Okay, and if you look at eta x of SL, what does it do? It does not move the position of the worker, but sorry, here it's a E, because I called E the. It does not move the E. Sorry. Okay. It does not move the position of the worker, but it switches the configuration at x by adding a Dirac mass at x. Okay. So if I come back to my picture, will I manage to do that? Let's see. Yes. If I come back to my picture, this was my configuration. Okay. If I multiply this configuration by, let's say, Wx by a work, it will not change it will not modify the position of the lamp, but it will modify the position of the worker. And if I multiply by this configuration by a lamp, I will just switch. I will not modify the position of the worker, but I will switch the value of the lamp at this position. Okay. So this is the lamplighter group. Now there is one Cayley graph which will be, it's an exercise that SL and WX, okay, where L is in Z over N, Zn, and X in gamma. This generates, okay, you take D, a generating set of gamma. Okay, so you start with some generating set for the workspace, which is symmetric. Okay, so which is finite symmetric, and it's an exercise that SLWX with L or possible position of the lamp and X in D generates lambda, the Lamplighter group. Okay, but we will not be interested by this Cayley graph. We'll be interested because their spectral measure is continuous, I think. We will be interested by a more exotic generating set, which is the switch walk generating set, which is a set of SL. You multiply the first switch and then the walk, which are called the switch walk, okay, with L in the lamp space. Okay, I call L the lamp space, and X in D. Okay, so this set is called this set of generating. This is a set. This is also a generating set. Is also a generating set. Generating set of lambda. Okay, so the interpretation is that what you do is when you multiply by an element of that guy, of this family of generating set, you first switch the lamp where you are, and then you move. There is also WS, which is another where you do the same, the inverse. You multiply first by you first move and then switch. It's also a generating set, which we call WS, and there is a third where you switch, you move, and you switch back. L prime in L, X in D is also a generating set of lambda. Okay, so this is the three generating sets of the Lamplighter group, which are going to be interesting for us. So this is a theorem that you can find in the paper of Grigorchuk-Zuk-Bus. Lehner-Neuheiser-Bus. Lehner-Neuheiser-Bus. Okay. It is the following. So you take n, you define p to be 1 over n. Okay, so this is, I recall n is the number of lamps. Okay, and you define per prime of gamma of p, which is a site percolation on gamma with parameter p. So we saw that last time. It means that you keep, it's a subset of it's a random graph where you keep one edge, where you remove all edges adjacent, you declare a site open or closed with probability p, or 1 minus p, and if the site is open, which happens with probability p, you keep all edges, and so if the site is closed, you remove all edges adjacent to p, adjacent to this site. Okay, so this is site percolation. And so this theorem, which is says that if you look at the Plancherel measure of the switch walk system, generating system, divided by n, okay, so where mu divided by t is a push forward of mu by the map. X gives x over t, so you just rescale your spectral measure by 1 over n. This is equal to the Plancherel measure of the system WS. This is also equal to the same system, but you have to rescale by 1 over n squared. And this is equal to the expectation of the spectral measure at the unit of the group of the site percolation graph with parameter p. Okay, so this theorem is very nice because it connects two apparently very different objects. One of them is a Plancherel measure, the spectral measure of a Cayley graph, and the other one is a random measure, is the expectation of a random measure, which is obtained by making site percolation in the group. Okay, so I will give a proof of this theorem, and then I will say why it was important to prove counterexamples of various conjectures on the regularity of spectral measures. Okay, so let's prove this theorem, because the proof is quite neat. So I will just prove that this is equal to that, okay? Because the two other cases are the same. So for ease of notation, I will denote my after this one. For ease of notation, I will divide by n. So I will call mu this rescale spectral measure, and I will call mu the spectral measure on the right-hand side. Okay, so the strategy would be to try to prove that the two objects have the two measures have the same moment. Okay, it is enough to prove that mu and mu have the same moments. Why? Because they are characterized by that moment, because they have bounded support. Okay, we have already saw that. Okay, so let's call WK. So the set of closed walks of length k from E to E. Okay, so E is in gamma. So in the Cayley graph, gamma d. Sorry. There is something which was not clear. Okay, so yes. So when I write, so it was not clear. I should write G, and G is a Cayley graph of gamma with a generating set D, which I fixed. Okay, so. Okay, so this is a G is this guy, and so here it's. Okay, so I have to, of course, to site percolation, I have to define site percolation, I have to define the Cayley graph I'm considering on gamma. And the Cayley graph I'm considering is a Cayley graph where I have associated to this fixed set of generators, which I've chosen at the beginning. Okay, which is in this graph. Okay, sorry about that. So again, you can write this is a set of gamma, what you write as gamma 0 up to gamma k, with gamma which belongs to the gamma power k plus 1, where successive edges gamma t plus 1 is an edge of gamma of G. For t equal to 0 up to k minus 1. Okay, so let's define the range of the range of gamma is a set V gamma, which is a set of the gamma t with t between 0 to k. Okay, so this is a set of visited vertices. So this is usually called the range. Okay, so let's start by computing the moments of mu. Okay, so let's start to compute the moments of the random measure perc prime g p. So here it's a g. So what is this equal to? So as I said at the beginning, this is so I keep confusing. This is a set of closed walk. You can write it as a sum. This is a set of walks on WK which are open. Okay, so you can write as a set of gamma in WK of the product from t equal 0 to k, but the indicator that gamma t is open. Okay, because it's side percolation, so you keep each edge is open or closed with probability p or minus p. So this is a set of walks in this guy. So I count all walks in G, and I will have to count them if all vertices which I visited are open. So there is this explicit expression. So if I take the expectation of that, okay, which is by Fubini the case moment of the measure I'm interested in, I have a formula. This is a sum over all paths. And then what is the product? I take the expectation here, I use independence, and then I will just get p power v gamma. Okay? Which is for our choice of gamma, n power minus v cardinal v. Okay, so that was the easiest part. I have computed the moments of the percolation graph. Now I should compute the moments of the Lamplighter graph. Okay, to do that, so I will use some notation. So it's, at least for me, it's easier to think about random walks. So A is the adjacency operator of my Cayley graph WS with my Cayley graph which I'm interested in. And P, which is d minus 1 times A, is corresponding transition kernel of the simple random walk on Cayley graph. Okay. So the moments of so I will recall you. The moments nu was the measure I'm interested in. So let me write it here. So moments of sorry, I made a mistake. Because the number of generators, it's d times n, because when I make a walk step, either I make a when I make a walk step, I have to make a switch steps. There are n possibilities. Okay, so the number of possible steps for the random walk on this Cayley graph is d times n. So since nu is only rescaled by n, the moments of d nu are d power k times the moments of the spectral measure of P, okay, which coincide to the you can interpret that as a probability starting from the unit of the group, but you are back at the unit of the group after k steps, where Sk is a simple random walk. Well, so S0 is epsilon, S1, Sk is a simple random walk on this group. Okay. And we can write St as being, so it's a pair formed by a configuration and a position, which we call gamma t. Okay, eta t, it's a configuration of lengths. And gamma t is the position of the lamplighter at time t. And I can write St, since I can write St, so as a product. So let's assume that I do a random walk on the right, for example. It's eta t gamma t, where xt, where the xt are id. They are sampled according, and xt, they have low, they are uniform on the generating set, so they are of the form w xt product slt with xt uniform on D and lt uniform on L, and both are independent. Okay. So gamma if I restrict, so gamma, if I look at the trajectory just on the position of the lamplighter, this is a simple random walk on my base graph G. And it is independent of the lengths of the SLTs. Okay, so because the walker moves, if you look at the walker moves independently of the position of the lamp, but the way the lamps are dated depends on the positions, successive position of the lamps. Okay, and eta t of y, if I want to see the dates, will be equal to eta t minus 1. The configuration at time t will be equal to the configuration at time t minus 1 if y is different from the position, from the next, so the current position of the walker, and it will be equal to eta of t minus 1 plus lt if y is equal to gamma t. Okay, so and you only update at each step. You only update the configuration of the lamps at the position of the walker. Okay, so it follows what? That to sk will be equal to epsilon. So if you start from the empty configuration with the position of the walker at the origin, sk will be at time k, you will be back to your position if gamma k is e. So if the simple random walk on G is back to e, it has turned back to the origin in the group, in the walk group, and there is this n, and the configuration should also be all lamps should be put to 0. So this will happen if and only if for all all positions which have been visited by the lamplighter at the last visit time, as the last passage time. So the last time that you visit X, so if the last passage time of X, let's call it Tx, you must have that this due to this relation here, that eta Tx minus 1 of, so it is X by definition, plus L.Tx should be equal to 0. Okay, so you will be back to the origin. You will be back to the unit of the group if and only if the position of the worker comes back to the unit of the base group, of the work group. And at the last time you have visited a lamp, you switch it back to 0. And this is what I've written here. Okay, but this event, at the last time you switch it back to 0, this happens with probability 1 over n, which is p. Okay, because whatever is this value, the value of the position of the lamp, there is only one choice of L for which the lamp which will be equal to 0, and by definition it has, since L has cardinal as n elements, it will happen with probability p, which is 1 over n, and this will be independently of the rest. Okay, so by rest I mean loosely the position, the works and the previous choice of the LTs, because the lamps, the LT, are independent. So to summarize, we have proved that the probability that Sk is epsilon is equal to 1 over dk sum over gamma. So this is because this is for this event, but I look at the probability that I am back at the work state, that I am back on the worker is back at the unit of the group. Okay, so this you have to sum over all closed works of length k, and each work has a weight 1 over dk, and this probability and the second event is probability p power v power gamma. Okay, and this is exactly the moments that we have computed for. This is exactly the moments that we have computed for these percolations. Okay, hence up to this scaling. This is 1 over dk times the case moment of d lambda. Okay, so we have proved this equality of moments. Okay, so let's come back to some. So you see, it's a nice probabilistic argument, which is I like it because it's quite unusual in a purely. There is no randomness at the beginning. It's only a group and computing a Plancherel measure, but the way you compute the Plancherel measure is based on a purely probabilistic argument. That's nice. So if you, so the original example of Grigor, Schuck, and Zuck, Grigor, Schuck, and Zuck was the case where the base group gamma was Z, okay, and n was equal to 2, okay, so L was 0, 0, 2. And they have computed explicitly the Plancherel measure. And if you divide it by 1 over 2, this is equal to the sum over all k of pk1 minus p, so p is equal to 1/2 here, of the spectral measure of a line segment of length k. Okay, because so this is Lk if you go from 1 to k. So this is a corollary. But if you apply this, if you specify this for the case of Z, what is, if you come back here, what is this? So the side percolation on Z is quite trivial. So it's just a disjoint union of intervals, where each interval has a geometric length of this length. Okay, and then the spectral measure will be the empirical spectral measure of the line, which we have seen as being mu of Lk. Is I think we have seen it. It's the Dirac mass at cosine of 2 pi k over n plus 1 for k equal 1 to n. Okay, so I encourage you to, it's a nice exercise to deduce from the theorem that is corollary. So in particular, it's purely atomic. It is purely atomic. It is purely atomic. Okay. So this was a surprise, and in the community, and also for the case of, I mentioned the problem of, it is also possible to compute when you take gamma, which is a free group, let's say, or gamma to be, I should say G to be the corresponding Cayley graph to be the infinite irregular tree, and n equal to 2. You can compute explicitly also, and general n, you can compute mu as an explicit form. The atom at 0 as an explicit form. I will come back to that. Okay. Okay, maybe it's a good time. If you have questions on this part, it's a good time to ask questions.
Excuse me.
Yes.
Could I have a notation question?
Sure.
Yeah, for the last theorem you mentioned, for the statement, you are writing mu SW, mu
yeah.
SW.
Yes. Yes, okay. It's, I should write. So it's a short. So yeah, so I should write. Okay, so with an abuse of notation. So maybe, okay, what I should do is I should probably define more so what I should do is mu of the Cayley graph of lambda with this generating set. You will be happy? Yeah,
yeah.
So it's just, it's much shorter.
Okay. Okay. Thank you. Yes.
You're welcome. Are there other questions?
Yeah, I think I understand. Yeah, this is what I asked.
Thank you. Yeah, I mentioned also yesterday quasi-transitive graphs. We will see them again appearing at on the second part of the course, of the lectures. Okay, so we will see that maybe I should mention it's a parenthesis. Quasi-transitive graphs. So we saw that transitive Cayley graphs was transitive graphs, and there is a nice way to define the Cayley quasi-transitive graphs. Quasi-transitive, I will call you, it means that the automorphism groups as a finitely many orbits. Okay, which is through what I called colored Cayley graphs or colored groups. What is that? It's you can define them simply by the adjacency matrix. So you take gamma, gamma G, which is a Cayley graph of some group with some symmetric set of generators. So we have seen that the adjacency matrix of the adjacency operator of A of the adjacency operator of this Cayley graph, you can write it like that, where the lambdas are the lambda of G on the left multiplication operator by the element G. And to get you can, if you have an operator of the form sum over all G in S of AG tensor lambda G, okay, where the AG are, let's say, matrices of size R, which are integer valued. Okay, so here you have an operator which is a bounded operator on C to the R tensor L2P. Okay. Okay, so here you define an adjacency operator, and if the AG are integer valued, okay, if the even are values in 0, 1, you can interpret that as adjacency operator is the adjacency operator of a quasi-transitive graph. Quasi-transitive graph. Okay, so I invite you to check that. So one way to define quasi-transitive graphs is by this, what I call colored Cayley graphs, because what you interpret the R coordinates, the coordinates here as being colors, okay, and to each, because an element on the vertex set, so it's the vertex set is V times the set of the set 1 to R, okay, so V, so it's gamma. Okay, so you see that as the vertex set is a group element, and you add to each group element a color, and then you use these matrices to define the adjacency in this graph, and you obtain a quasi-transitive graph on this vertex set. Okay. Okay. So now we will come back to. We'll start to do. We are done with the Cayley graphs, at least with what I wanted to say on Cayley graphs. Now we study, I mentioned one of my motivation was to study the spectral measure of large finite graphs, and for that there is the good framework, as we will see, is a notion of Benjamini-Schramm convergence. Okay. So which I will not define. So the goal now is to define a spectral measure of unimodular graphs. Okay, so we have seen that for finite graphs, when you are taking the spatial average of the spectral measure at the spatial average of spectral measure at the point at the vertices, you obtain the empirical density of the eigenvalues. Okay, and this way we could define a spectral measure which was independent, which was unitary independent. Okay, which didn't depend on. It didn't depend on the eigenvector basis. We could do the same trick for transitive graphs, because the spectral measure, even for transitive graphs, or for example Cayley graphs, because the spectral measure do not depend on the spectral measure at Dirac masses do not depend on the choice of the vector. So there is a kind of broader category, which are unimodular graphs, where it is possible to do that. Okay, so but before introducing those are called the unimodular graphs. So, but before introducing them, I should speak about this Benjamini-Schramm topology. Benjamini-Schramm topology. Okay. So first definition, what is a rooted graph? So a rooted graph, so we saw it last time, but I repeat it, is a connected graph. G is a connected graph. And O is a vertex of G, so we call the root, the distinguished vertex. Okay, so the advantage of when you have a rooted graph, you can define GOT, okay, as being the restriction of you have an origin, okay, is a rooted graph spanned by vertices at distance less or equal than t from O. Okay, so you just, it's a subgraph G if for t, let's say an integer, for t an integer, it's a subgraph of your rooted graphs where you only keep the vertices which are at distance at most t from the root. Okay. There is a natural notion of isomorphisms of rooted graphs. You say that G1 rooted at O1 and G2 O2 are isomorphic if there exists phi, which goes from the vertex of 1 to which is a bijection. So they should be isomorphic as graphs. So phi of G1 is G2, and to be isomorphic as rooted graph, it should also send the root of G1 to the root of G2. Okay. Sorry, 1 second. So you can define an equivalence relation on graphs, on rooted graphs. So by this rooted isomorphism, and you can define G at the bullet here, the set of equivalence classes of locally finite rooted graphs. Okay, so what is this is called in combinatorics, this is called an unlabeled locally finite graphs. Locally finite graphs. Okay. Unlabeled, meaning that when you take an equivalence class, what you do is you remove the names of the vertices. Okay, that's why it's called. This is the information you have lost. Okay, so that's why you call that, in combinatorics, we call them the unlabeled graph. Okay, so it's just an equivalence class of rooted graphs. Okay, so they can be maybe sometimes, if V is a countable set, I will denote by, so I put a hat to remember that maybe I should not put a hat, but more stuff like that to remove. So this is an equivalence class. This is up to equivalence class. so it's quite boring, cumbersome to study unlabeled graphs. So sometimes we put labels, and so this will be the set of locally finite graphs, locally finite rooted graphs with vertex set V. Okay. Maybe we can also put n root O. So there is a way to move from when you have. So as I said, it's cumbersome to study unlabeled graphs. So usually there is some canonical way to. So there is a canonical way. A canonical way to label the vertices of an unlabeled graph. Okay, so meaning by that there is a way to put labels on two rooted graphs in such a way that if they are isomorphic, they will receive the same labels. Okay. So sometimes, as I said, it's easier to work with rooted graphs, so with labeled graphs. So you should not focus too much on this notion of unlabeled graphs. Okay, so but there was less an interesting family of graphs. Okay, and so when you have this set of labeled graphs, you can put on them a metric which will make them complete metric spaces. Okay, so this is a local you define a local distance if G and G prime, let's say G and G prime are in G tilde, you define the local distance between G and G tilde. Okay, so G is again a pair between a graph, and it's a pair given by a graph and a root. Okay, you look at the sum over all t, which goes from 0 to infinity. You define this distance 2 minus t of the indicator, but the restriction of G to the t neighborhood is equal to the restriction of G prime to the t neighborhood. Okay, and you can also define the same thing for rooted graphs if you want, and then the local distance would be the same. Okay, it extends directly. And there is a lemma that when you embed such spaces with the local distance, you obtain a complete metric space. Complete metric space. It's also separable. So probabilists love separable complete metric space because when you have such one, you can also the set of probability measures on. So when you consider the set of probability measures on such space and equipped with the weak topology, you obtain again a complete metric space. Okay, so that's what we do. You define P, you consider the set of probability measures on G tilde, on G. And you equipped with the weak topology. Okay, you can do the same for the set of probability if you want. If you have some reference of a vertex set, you can do the same, because this is also true for. This is also true for the notation orbit. It's also it's complete metric space. Okay. So this is, since we are in a discrete setting, it's easy. So if rho n, so if you take a sequence of measure in, let's say, unleveled, a sequence of random rotated graphs, you will have that rho n converge to rho weakly, where rho also is such measure, if and only if and only if, for any t integer, for any g, which is so this is not this notation, or maybe I can remove it. The mass rho n of g of t converges to rho of g of t. Okay. So this is so it's to check that you have weak convergence. It's enough since we are in a discrete setting to check that the law of the mass that you put on t neighborhoods for converge. Okay. So maybe I will introduce a notation. If so, I will denote by expectation of rho. So I will denote by rho n of gt. I will write it. I will indicator that g0 of t is equal to gt. Okay, so when I will write expectation, I will write the measure, the corresponding probability measure. I will write it here, and a canonical and a sample of the rotated graph will be denoted by always by G. Okay, so this is the notation. So we are not interested at the beginning with rotated graphs, but we are interested by unrotated graphs. Okay, so this is where this was the local topology. So this is where the Benjamini-Schramm arrives. So for a finite graph, G, okay, you can define there is a natural measure on random rotated. There is a natural random rotated graph that you can associate to it. Okay, so we denote by G of V. Okay, the rotated graph rotated at V. So V is a vertex. Rotated at V. Okay, and maybe my notation is not great, and G, no, maybe, okay, also I will change my notation. So my notation was too bad. For V in V, let's denote by G of V, the connected component, the connected component of G restricted, sorry, G restricted to the connected component of V. Okay, so G of V, because the graph is not necessarily connected. So when if you have a vertex, you just look at the connected graph, which is the connected subgraph of G, which contains V. Okay, and we denote by G of V, which is the equivalence class of G of V rooted at V. Okay, so this is an element of G tilde. Okay, right. So now I can define U of G, which is the law of G of O with O uniform on V. Okay, so I can write it as 1 over cardinal of V times sum of V in V of Dirac mass at the G. So this measure U of G plays a central. This is plays a central role in this Benjamini-Schramm convergence theory of graphs. Okay, but before doing that, let's make an example to be sure that everybody has understood. So let's assume that my graph is this is G. Okay, so G has labels. It's a label graphs. It has some vertices. Okay, what is U of G? What is U of G is 1 over 5. Okay, maybe I will not write. What is G of 1? G of 1 is this guy. I can represent it. G of 2 is equal to G of 4, and that's, I can represent it this way. So you see, I remove the vertices. I just point the roots, so because they are unlabeled graphs, and what is G of 3, which is equal to G of 5. This is this graph. Okay? So you see the information that we have lost is we lose the name of the vertices, and we only look at the graphs in the connected components. Okay, so this guy is an element of the probability measure. So now I take the empirical measure of this and I obtain U of G. Then the definition, a sequence of graphs of finite graphs. GL converges in the Benjamini-Schramm sense to a random rotated graphs with low rho if U of Gn converges weakly to rho. Okay? So this is the definition of the Benjamini-Schramm convergence. Okay, so this is a very rustic. So in other words, if I want to be Gn converges in the Benjamini-Schramm sense to rho if for any t and g, if you take any unlabeled rotated graphs, 1 over cardinal of V of Gn times the sum over all vertices. That's the indicator that the graph G, so maybe I can, the equivalence Gn V rooted V is isomorphic to the rooted graph GnV. It's isomorphic to G. This converges to the mass and the probability against rho at GO. So I should put it here. GOT. Maybe I can put it here. Okay. By extent, so this I just repeated the definition, but it's kind of more concrete written in this way. By extension, so as I told you, I warned you, it's cumbersome to work with unnable graphs. If rho is a probability measure on some rooted graphs, okay, on some set of some origin. Okay, maybe I skip the idea of right origin. We say that Gn converge in the Benjamini-Schramm sense to rho if Gn converges to rho tilde, where rho tilde is the corresponding measure where you remove the label. It's a law of the equivalence. It's a law of the equivalence class. Okay. I think you have understood. But rho tilde is a measure, is a law of, is a push forward of the measure rho through the equivalence class, through the equivalence relation. Okay. Let's give some examples. Yes. Let's give some example of convergence in the Benjamini-Schramm sense. Let's start with the cycle Cn. So where it converges the Benjamini-Schramm sense to what? Can someone tell me? What does it converge to? Does someone dare to take the... Okay, so it converges to a Dirac mass at Z rooted at 0. Okay, so it converges to the infinite line, to the bi-infinite line. Okay, because if you look at any given vertex, you look at its neighborhood, you will not see you should check this convergence for any fixed t. So if you fix t and let n goes to infinity, you will not see that you will not make the difference. You will not see the cycle. You will just see a portion of the infinite line. For the same reason, if you take a line segment, it also converges in the Benjamini-Schramm sense to a Dirac mass sense. Okay. The Benjamini-Schramm distributed convergence is also does not see also the connected components. So if you have a disjoint union of cycles, okay, where each of them, so if you add copies of Cn and so on, this graph will also converge so if you take multiple copies, if each of the cycles goes, if the length of each cycle goes to infinity, this will also converge to Dirac mass at 0. So the fact that the limit, so you do not see any information on connected components, on a number of connected components through the Benjamini-Schramm topology. Okay. If Gn is a d-regular graph on n vertices, say, and whose girth gamma n goes to infinity. So this is a girth, which is the length of the shortest cycle. Okay, so if you have a sequence of graphs such that the smallest cycle is the smallest cycle goes to infinity, the length of the smallest cycle goes to infinity, then you will not be able to make the difference for the very same reason between Gn when you restrict to a T neighborhood, because you will not be able to make the difference between the T neighborhoods of Gn and the T neighborhood of the infinite tree with the vertices. Okay, so Gn rooted at any vertex x. Okay. And are isomorphic, will be isomorphic to the T neighborhood of the infinite irregular tree if T is less than gamma. Okay, so where TD is the infinite irregular tree. Okay. So it implies that U of Gn will converge to direct mass at TD. Okay. So these are examples. Every time you converge to a direct mass, but this is obviously not always the case. This is more an exception. Let's consider, for example, so this is let's consider a new example where you consider you look at the infinite irregular tree. At depth n. Okay, so you define Gn to be Td restricted to its T neighborhood, to its n neighborhood. Okay, so we take D to be at least 3. Okay, so this is Gn. So you take, so you have the origin of the, so you should not go. So you look at the T regular tree, here is 3 regular tree, and you cut everything which is a distance at most beyond n of to the roots. Okay. So where does it converge to? So there is a wrong answer, which is that it converges to the infinite irregular tree. It's not the case. Okay, why is that? Because most of the vertices are close to the boundary. So you see the boundary. So here, obviously, you are when you root it here, you don't see the difference. Or here, close to the root, you don't see much of the difference between the infinite irregular tree and your truncated tree. But when you are close to the lips, you really see the difference. Okay, and most of the vertices lies here. Okay, so this will converge to what is called the canopy tree. Okay, which is a random rooted tree. Which is a random rooted tree, which you can define as follows. So I make a picture of this tree. I look at this. I define. I make a picture. I make a picture of this tree seen from the leaf. Okay, so what I see is something like that. And so on. So here I have, okay, so if I make a picture of this tree, here I have a binary tree of depth 1. Here I have a binary tree of depth 2, and so on. I will have a binary tree of length 3, and so on. Okay, so this is a deterministic tree. But now I will put the root as random on this line according to some geometric distribution. Okay, so the position of this, so this I call it 0, 1, 2, 3, and so on. And you put the position of the root uniform at random according to a geometric distribution. Okay, so a geometric distribution of parameter whatever d, I think. Okay, p well chosen. I forgot. Okay, so I encourage you as an exercise to define properly this canopy tree. Okay, which answers the question to what is it. So this will be a random tree because the root this will be a random tree, a random rooted tree, which is this tree seen from the leaves, this irregular tree seen from the leaves, and where you put the root uniform at random according to some geometric distribution. Okay. So it's not always the case. Okay, so you see the fact that we take the root uniformly at random is crucial here. Another example, which is this L.2 random graphs. So G and P D over N. Okay. So the vertex set I will call you are the set first n integer, and each edge is present independently with probability d over n. Okay, okay, minimum with 1. And if d is fixed, and you let's call it Gn, so now u of Gn, since Gn is random, it's random. This is a random measure, and almost surely, as n goes to infinity, so here d is fixed, this will converge to a Galton-Watson tree with Poisson of spring distribution. So I will call it a Galton-Watson tree with Poisson d of spring distribution. What does it mean? It means that this is a Galton-Watson tree. So this is a tree associated to, so I sample the root as a number of offsprings with distribution Poisson d, and all offsprings have a number of offsprings, sampled independently with the same distribution. Maybe more generally, there is this configuration model. If you take D1, if you take a sequence of integer, so maybe you take a sequence of integers such that the sum of di is even, and di, and for example, sum of di squared is bounded. So this depends. So this sequence, maybe I should put an n here, does allows to depend on n. Okay. Okay, and the degrees is this di, they do not grow too fast. Okay, then you can define a graph. You can define, for example, you can define a multigraph which is called the configuration model, which is an important family of random graphs, where you associate to one D1 alpha edges, or directed to two D2 alpha edges, and to n dn alpha edges. Okay. And then what you do is that since the sum of these alpha edges is even, you can consider a uniform pairings or a uniform matching of this alpha edges. Okay, consider a uniformly sampled pairing or matching of the alpha edges. Okay, and when you do that, you obtain a random graph, which is called the configuration model associated to the degree sequence D1. Okay, so it's a random multigraph. Multigraph because you may have loops or double edges, and it is interesting because you have where the degree of the degree of a vertex x is precisely the x for all x in 1 to n. Okay, so it's a way to sample a graph with a given degree sequence. And okay, I will not do a course on random graphs, but under this assumption, for example, this measure is contiguous to the. You could also it's also a way to sample a uniform graphs with this degree sequence. Okay, so this family of graphs. So let's call it Gn. Under this assumption, U of Gn almost surely converge to also a Poisson-Galton-Watson tree, which we call the unimodular Galton-Watson tree. Sorry, I've forgotten an assumption. Assume that the degrees, the empirical degrees converge to some measure P. Okay. Which will be a Galton-Watson tree with degree distribution P. So this is called the unimodular Galton-Watson tree with degree distribution. P. How is it defined? So the root has distribution P, and then the offspring sends it. So it's a size bias. So you define P hat of K, whose distribution is K plus 1. So it's a size bias of P. So so the root has distribution P, and all other vertices have a number of offspring samples independently of probability P hat. Okay, so it's a Galton-Watson process. It's a Galton-Watson tree. The only trick is that the degree has not exactly the same number of offsprings as the other measure. Okay, note that if you do the size bias of Poisson with parameter D, you also obtain Poisson. Okay. Or yes. Okay, so if you want to know more about this convergence, you can look, for example, there is a monograph. See, there is a monograph by Remco van der Stadt. I'm not sure of Stadt. Yes. But you can see on his webpage, you can find a book where he proves these statements. Okay, so this was so as we will see, so it's a very rustic mode of convergence, so Benjamini-Schramm convergence. But what is very surprising is that there are a lot of functions, graph functionals, which are continuous for this topology. And the reason I mention it in these lectures is that the spectral measure is one of those. Okay, so that's what I'm going to explain. But before that, I will also need two definitions. There is one property, unimodularity, not all random rooted graphs can be Benjamini-Schramm limits of a finite sequence of graphs, okay? And in particular, they should satisfy an assumption which is called unimodularity, which I will not produce. Okay, so let G, so now I put two dots, be the set of unlabeled doubly rooted graphs. So it's a graph G with two roots, X and Y. Okay, and the roots are ordered. Okay, X, it's not a pair, it's so you have two distinguished roots and the rest of the graph. So you can also define the local topology. The local topology is defined the same way, except that now you look at the t neighborhoods of each of the roots. Now you have two distinguished roots. Okay, it's also complete separable metric space. Okay, and then you will say that a function rho, a measure, now definition, a measure rho on random rooted graphs is unimodular if for all non-negative measurable functions f, so on double rooted graphs 2r plus, we have that the expectation against rho of the sum of the vertices of the graph G of G O B is the expectation of rho of the sum of f of G V O. Okay, so what I've done, I will comment on this equation. So you can interpret, so you say that you can interpret, so what I've done, I just switched the position of the root in the sum. So here it's the first term, here it's the second term, okay? So this is called the mass transport principle. This is called the mass transport principle. Because what is the interpretation of that? So there is a very nice survey by L.2 and Lyons on unimodular graphs. So what is the meaning of that? you can interpret F as an F of Gx. If you interpret that F of as a mass sent from X to Y along the graph, okay? So what is on the left-hand side, it is the set of the total mass that the root sends to the rest, to the network, to the graph. What is it? And on the right-hand side, this is the total mass that the roots receive. And this mass transport principle says that it's a kind of conservation of mass principle, that the total mass in expectation, the total mass that the root sends is equal to the total mass that the root receives. Okay? And if G is finite, then U of G is unimodular. So this is a lemma, maybe. Okay, so if a graph is finite, the U of G is unimodular. This is easy to check. It's simply indeed proof. So you take such function. So what is the expectation with respect to U of G of the sum over all V of F of G O V? This is by definition 1 over cardinal of V, maybe simply denoted by V of G, okay, of the sum of all vertices of G, of the sum of vertices which are in the connected components, because I recall you that when you take U of G, you only consider the vertex in the connected component. So I will denote it by V of U of F of G of U V. Okay, so this is the graph spanned by the connected. This is the connected components, and this is the definition. Okay. Now you switch U belongs to V of U. It's sorry, V belongs to V of U. It's equivalent to U belongs to V of V. Okay, and the same with G of U. And G of U will be equal to G of V if U and V are in the same connected component. Okay, so you can certainly write. So here, if I want, I can switch. I can write that as a sum over all V in V, the vertex of the graph, of the sum of the U which are in the connected components of V. Okay, maybe I should not, it would be more clear if my graph, I should maybe not make. Okay, maybe this notation is more clear. If I put an index here. And then it's the function of G of, if U is in the connected component of V, then G of U is equal to G of V. So I can put a V here, and here I can put, there is U and V. Okay, so, and if you, this is precisely the expectation of U of G of the sum over all V in V of F of the sum over all U in V of F of G U of. Okay, so this is simply I've simply switched its full meaning, finite full meaning. Okay, I should conclude. So there is this the set. There is some definitions which I will conclude on that. So a measure rho in a random rooted graph is sophic if there exists a sequence of if there exists a finite sequence of graphs, such that U of Gn converges to rho. Okay. So in other words, sophic is a closure of the set of U of G, which is finite. The terminology sophic comes from Gromov. If you want more background, I encourage you to look at the reference of L.2 lines. Okay, so the closure of all sophic measures, of all U of G, finite U of G, is called sophic. Okay, and there is a lemma which says that the set of unimodular measure, the set of unimodular measure is closed for the weak topology. Okay. So a corollary is that the sophic, in particular, the set of sophic measure so I will notify it like that, sophic. The set of sophic measure is included in the set of unimodular measure. There is no known example of unimodular measure which is not sophic, so the converse is open. The answer is probably no, but we don't know. And it's a vast open question. Okay, I will not mention more, but it's obviously a very, very difficult question. Okay, so next time we'll continue. I will mention now the link between the. We'll see that for sophic measure, in particular for unimodular measure, so in particular for sophic measure, which are the measures which we are primarily interested in, there is this analog of this spectral measure, which is this empirical distribution of eigenvalues, and which satisfies all nice continuity properties that we want with respect to the Benjamini-Schramm topology. Okay, so I think that's time to stop, and if you have questions, we'll be happy to answer them.
Any questions?
Yeah, I think that this question of sophic measures, are all unimodular measures sophic? It's equivalent to the cone embedding problem. So it's really a kind of top open problem in the math community. But since this, so it's, yeah.
Yeah. Well, thanks a lot for your very nice lecture. And so just to recall, I sent a message to, so maybe if some people arrive late, I will just repost it once more. So in the chat, the instructions for people who want credit. So here it is. And so tomorrow there is no lecture, and the next one is Thursday, right? So,
Yes.
So, well, if there are no more questions, thanks a lot, and see you in 2 days.
See you. Bye-bye.